Hey friends, welcome back. MLflow Prompt Registry, persistent memory, and Databricks Apps as agent UIs is one of those topics where a single qualifier word changes the answer. Today we'll see exactly why. Let's get into it. By the end of this video, you'll know how to ship prompt changes without redeploying code, how to give your agent memory that survives a restart, and how to put a real user interface in front of it without leaking a token to every browser on the internet. 3 capabilities, 1 production stack. In episode 12, we walked through the canonical deployment path, PyFunk wrapping, Unity catalog registration, and model serving for the agent itself. Then in episode 13, we covered Model Context Protocol Servers, or MCP, and how the agent reaches its tools without leaking secrets. Today we're closing 3 gaps that remain: the prompts the agent uses, the memory it keeps between turns, and the user interface sitting in front of it. 5 terms anchor today's video. The MLflow Prompt Registry is the Unity catalog-backed home for prompt templates, with versioning and commit messages. A prompt version is immutable and numbered. An alias is a mutable named pointer like production or staging, and the difference between them is the entire gated release story. Lakebase is managed serverless PostgreSQL inside the Databricks workspace, designed for agents and apps. The Databricks Apps service principle is the unique machine identity each app gets automatically, and on behalf of authorization, or OBO, is the flow where the app forwards a signed-in user's identity so downstream calls run as that user. A guide at DataDino emails the team on a Friday afternoon. The K-12 tour descriptions have stopped including dietary notes, and the kids are noticing. The team starts hunting. The prompt template lives somewhere across 3 GitHub repos, and nobody is sure which one. There's no version history attached to the prompt itself, no commit message that says what changed and why. While they're digging, the chat thread in their internal demo UI disappears because the Flask server restarted, and a junior engineer points out something worse. The JavaScript in that UI has a Databricks token sitting in a constant, visible to anyone who opens browser dev tools. That's 3 problems in one afternoon, and Databricks has a first-class answer for each. Here's the shape of the video. Prompts need a lifecycle, versioning, promotion, rollback. Agents need memory that survives a process restart. And the user interface in front of an agent needs a real authentication story, not a token pasted into a browser. The MLflow Prompt Registry, Lakebase, and Databricks Apps each replace a hack that production teams use to ship. We'll take them one at a time, then tie them together with a continuous integration and deployment pipeline at the end. Start with the prompt problem. When your prompt template lives as a Python string in source code, every change to that template is a code change. The commit message belongs to the surrounding code, not to the prompt itself, so there's no clean record of what the prompt looked like a month ago. There's no governed registry, no Unity catalog lineage, and no rollback story that doesn't involve a full code revert and a redeploy. And the worst part, when a regression hits production, the time to fix is gated by your CI pipeline, not by your data. Here's the registration call. MLflow.GenAI.register prompt takes 3 things: a name that follows the 3-level Unity catalog convention, a template with double brace placeholders, and a commit message describing what changed. That commit message is the piece teams skip in source code and regret later. Notice the placeholders use double curly braces. That's the registry's templating syntax, distinct from a Python f-string, because the app will fill those in at runtime. 4 things happened in that one call. The registry created a new auto-incremented version under the 3-level Unity catalog name. The template went in with its double brace placeholders preserved. The commit message was attached as audit metadata, visible forever to anyone with read access, and the returned version number is the immutable identifier. It will refer to exactly that template string for the lifetime of the catalog. Here's the architectural guarantee at the heart of the prompt registry. Once you create a version, it cannot be modified, ever. That's not a soft guideline. It's a hard rule baked into the service, and it matters because immutability is what makes rollback meaningful. If version 3 could change under your feet, then reverting to version 3 wouldn't actually reproduce yesterday's behavior. Because it can't change, version 3 always means the same template every single time you load it. Here's the duality. On the left, a version is numbered 1, 2, 3, 4. It never changes once written, and it's the audit-safe identifier you'd pin in a research notebook. Think of it as a git commit SHA. On the right, an alias is a name, dev, staging, production. It's repointable to any version, and moving it doesn't require a code change. That's a Git branch name. Same mental model engineers already use every day. 3 shapes of URI, and the one your app uses tells the story. The first is mutable, prompts :/name at alias. That's what apps in production load, because moving the alias automatically swaps the template the app uses. The second is immutable, prompts :/name/version. That's what an offline evaluation pins, because you want yesterday's evil to mean the same thing tomorrow. And the third is reserved, at latest. You cannot redefine that one. MLflow always resolves it to the highest version. The Databricks guidance on this is 1 sentence long. Configure your apps to load prompts using aliases rather than hard-coded versions, because that approach enables dynamic updates without redeployment. That's the entire reason aliases exist. If your app code says load at production, then promoting a new version is just moving the pointer. The app picks it up on the next request. No rebuild, no restart, no CI pipeline. Picture a stage curtain. Backstage, you have versions 1, 2, 3, and 4 rehearsing, each one fully written, each one ready to go on. The audience only ever sees whichever one the production rope is tied to. Promoting a new version is pulling the rope. Rolling back is pulling it the other way. You don't fire the actors and recast the play every time you want to change what the audience sees. You just move the rope. The full release flow has 5 beats. First, register version 4 with a commit message. It's auto-incremented and immutable from that moment on. Next, point the staging alias at version 4. The staging app picks it up automatically. Then, run your evaluation scorers against the staging alias on production-shaped traffic. Once the evils pass, move the production alias to version 4, no redeploy. And if something regresses in production, rollback is just one more call. Move the production alias back to version 3. The time to recovery is a single API call. 2 calls to set prompt alias is the entire promotion ceremony. First call points staging at version 4, where evaluation runs. Second call points production at version 4, where users land. Rollback is symmetrical, same function, different version number. There is no rebuild, no container push, no rolling restart of the app. The app already loads at production, and the registry just answers with a different template the next time it asks. Here's why Git-Versioned prompt files cannot clean up after themselves the way the registry does. On the left, every change is a code change. Every fix requires a redeploy. There's no Unity catalog lineage on the prompt itself, and rollback means a revert plus CI plus a redeploy, minutes at best, hours in practice. On the right, prompts are versioned independently of the code that uses them. Moving the alias takes effect immediately. Governance lives under the Unity catalog 3-level name, and rollback is one API call. Gated release with rollback is what the alias mechanism is built for. Git can't do this cleanly. Prompts have a governed home, a versioning story, and a one-call rollback. That's the first deployment gap closed. Now the second, when the user closes the laptop and comes back 20 minutes later, where does the agent remember what they were talking about? The first instinct most teams have is a Python dictionary inside the agent process. Thread_ID maps to the conversation so far. It works in a notebook. In production, it breaks 4 ways. Every restart wipes the dict. Scale out across multiple replicas means each replica has its own dict, and the user lands on a different one each turn. Scale to 0 wipes everything between idle periods, and the user-facing symptom is an agent that asks the same questions over and over because it has no idea what was said 2 minutes ago. Lakebase is managed, serverless Postgres that runs inside the Databricks workspace itself. It has native OAuth authentication for service principals, no VPC peering to configure, and no firewall holes to punch. It's the durable store you point your agent at when in-memory dictionaries stop being acceptable. You could run any Postgres anywhere. Here's what Lakebase gives you that a generic Postgres doesn't. It's built on the Neon engine Databricks acquired, so it inherits serverless scale to 0 and instant branching. The app's service principal mints short-lived OAuth credentials at runtime. No password lives in your code, your environment variables, or your secrets manager. Because it's inside the workspace, there's no peering, no firewall hole, no extra network hop, and Lakehouse Sync automatically replicates your Lakebase tables to Delta in Unity Catalog, so chat logs become queryable for BI without you writing an ETL job. Memory comes in 2 flavors and they're both worth a thought. Short-term memory is per thread, checkpoints, scratchpads, the agents running notes during one conversation. It's keyed by thread_ID, and a common pattern is the lang graph checkpoint Postgres library pointed straight at Lakebase. Long-term memory is per user, preferences, cross-session facts, things you want to remember next week. It's keyed by user_ID, in custom tables, in the same Lakebase instance. Both flavors stored in Lakebase. The schema differs, the access pattern doesn't. Trace the flow. The user is in a browser. They hit the Databricks app, which is the front end. The app calls the agent endpoint, which is your model-serving deployment from episode 12. The agent reads and writes its current state to Lakebase. That's the OLTP side, low latency, per thread checkpoints. Then Lakehouse Sync replicates Lakebase tables to Delta in Unity Catalog automatically. The BI team queries those Delta tables from ASQL warehouse without ever touching Postgres. Same data, 2 engines, each optimized for its job. Picture the agent's office. Lakebase is the working desk, fast scratch surface for whatever it's doing right now. Delta is the filing cabinet down the hall, slower to reach, but where everything ends up for long-term storage, audit, and analytics. Lakehouse Sync is the assistant who walks paperwork from desk to cabinet automatically, on a schedule, without anyone asking. On the left, 4 patterns to avoid. A Python dict inside the agent process, wiped on every restart. A Spark data frame as session state. Spark is a batch engine, not an OLTP store. External managed Postgres reached over VPC peering, works, but expensive operationally and slow on cold paths. And a hard-coded Postgres password in environment variables, a credential failure waiting to happen. On the right, the corresponding right answer. Lakebase keyed by thread_ID service principal OAuth minting short-lived credentials. Lakehouse Sync to Delta for analytics. And don't forget the grant, the app's service principal needs can use on Lakebase, or the agent can answer but can't remember. 2 gaps closed. Prompts are governed in the registry, promoted by alias, immutable per version. Memory is persisted in Lakebase and synced to Delta for BI. The third gap is everything that sits between the user and the agent, the actual user interface, and the authentication that makes it safe. Here's the pattern we want to retire. A team stands up a Flask server or a Node app on a virtual machine, writes some JavaScript that calls the agent endpoint, And to make that call authenticate, they paste a Databricks token into a JavaScript constant. There's no governed identity for the app. Auditors looking at Databricks access logs see token activity, not app activity, and can't tell which app made which call. Every restart loses the chat thread. Every developer spins up their own VM. This is the hack that Databricks Apps is designed to replace. Databricks Apps is a managed runtime for web applications, Streamlit, Gradio, Flask, Node, hosted directly inside the workspace. You bring the code, the platform brings the runtime, the identity, the authentication, and the governance plane. It's a first-class deployment surface for the user interface in front of your agent. From the docs, each Databricks app has a dedicated service principal that acts as its identity when it accesses Databricks resources, unique to the app instance and not reusable across apps. That's important. You can't share one service principal across 3 apps. Each app's audit trail is its own. Each app's grants are its own. And the moment you delete an app, that identity goes with it. 2 authorization modes, and the choice between them is a real architectural decision. On the left, the app's own service principal, its machine identity, OAuth machine to Databricks resources. Audit logs say the app accessed something. Use this when every user of the app sees the same data. On the right, on behalf of, the app forwards the signed-in user's identity. It does that by reading the X-forwarded access token header at request time. Audit logs then name the actual user, not the app. Use this when Unity Catalog permissions differ per user, when the answer to who can see what depends on who's asking. Think of the service principal as the building's master key card. Everyone who enters uses the same card, and the logs all just say the app entered. OBO is the turnstile that reads each visitor's own personal badge. The logs say which user opened which door, and the door won't open if their badge doesn't allow it. Notice where the workspace client is constructed. It's inside the request handler, inside the function that runs when a user hits the /ask route. We pull the forwarded OAuth access token from the request headers, build a client scope to that user by passing the host and the token directly, and call the agent endpoint. The call runs with that user's permissions, and Unity Catalog enforces their grants on the underlying vector index, tables, and tools. The whole pattern hinges on doing this per request, not at startup. The on behalf of client depends on a user token that only exists once a request arrives. If you try to construct it at app startup, there is no user yet, no header has been forwarded, and the initialization code crashes before the app can even pass its health check. The rule is straightforward. Construct the on behalf of client inside the request handler on every single request, using the user header that arrived with that request. Scopes are the third piece. They enforce least privilege. You configure them in the workspace UI under the app settings, or programmatically through the REST API. Examples include SQL, serving.serving endpoints, and vector search.vector endpoints. The first time a user opens the app, they see a consent screen listing exactly which scopes the app is asking for. Here's the important part. The app can never exceed its declared scopes, even if the user signing in has broader workspace permissions. Scopes cap what the app can do, and user grants then narrow it further. Let's walk through a scenario in exam shape. DataDino's curator team wants an internal chatbot over their exhibit notes. The company uses corporate single sign-on, and curator notebooks have different read permissions depending on who you are. Junior curators don't see senior staff's draft research. Those per user Unity Catalog permissions need to hold all the way down to the vector index. The question is, when the app's backend calls the agent endpoint, what does it send in the authorization header? On the left, the right answer. The backend reads X forwarded access token from the incoming request, calls the agent endpoint with that user's OAuth token using the on behalf of pattern. Unity Catalog enforces the per user index access automatically, and the audit trail names the actual user who asked the question. On the right, the wrong answers, and notice they're all plausible, which is why the scenario question is hard. A personal access token pasted into a JavaScript bundle, the app service principle used for everyone, which loses the per-user enforcement the scenario required. The backend storing users' passwords. A virtual machine with a shared bearer token in environment variables. And the documentation is blunt about this. Personal access tokens are not supported for Databricks apps. It's not a recommendation. It's not a best practice, it's a hard rule. Invocations require an OAuth bearer token. Any answer that involves a personal access token reaching a Databricks app is automatically wrong before you even consider the security implications. Let's be clear why storing a personal access token in browser JavaScript is a real production security failure, not just a wrong exam answer. Any visitor to the app can open browser dev tools and read the tokens straight out of the network tab, or out of view source, or out of the JavaScript bundle itself. The default personal access token lifetime is up to 730 days. That's 2 years of workspace access from a single leak, unless an administrator notices and revokes it. The token carries whatever scopes the issuing user has, which in practice is almost always far broader than the app actually needs. And on top of all that, Databricks apps don't accept personal access tokens anyway. OAuth bearer is required. So the pattern fails on 3 different axes. It's wildly insecure, it grants too much, and it doesn't even work. The visceral picture. A personal access token in browser JavaScript is like printing your house keys bidding pattern on a billboard out front. Anyone walking by with a camera can cut a copy and let themselves in. Browser dev tools are that camera, and every single visitor to your app has one built into their browser. And in case any of that is ambiguous, Databricks recommends using OAuth instead of personal access tokens for user account authentication, because OAuth provides stronger security. The personal access token documentation now lives under a legacy heading. The direction of travel is clear. All 3 pieces are on the table. Prompt Registry gives us governed prompt lifecycle and gated release. Lakebase gives us durable OAuth-native memory for the agent. Databricks Apps gives us a user interface with a real identity and per-user authorization. One scenario remains. How do you ship all 3 from dev to prod together in a repeatable, reviewable way? Databricks asset bundles are how. One YAML file declares the agent, the vector search index, the model serving endpoint, the app, and any other Databricks resources you need. The Databricks CLI reads that bundle and deploys the whole topology together, with environment-specific overrides per target. The Databricks documentation frames the value of asset bundles around 4 properties: reproducibility, portability, automation, and configurability. In practice, that means the same bundle definition can move from dev to staging to production without rewriting it each time. It's infrastructure as code for the Databricks resources your agent depends on, deployed through CI instead of console clicks. Here's the shape of a Databricks asset bundle. Under resources, we declare a vector search endpoint, a vector search index whose name is parameterized on a catalog variable, and an app whose source code lives in a subdirectory. Under targets, we declare 2 environments. The dev target sets the catalog variable to DataDino_dev. The prod target sets it to DataDino_prod and turns on production mode. Same bundle, same resource shapes, different catalogs and different service principals. The promotion flow for a Databricks asset bundle has 4 beats. First, run Databricks bundle deploy with target dev that creates the index, endpoint, and app in the FE catalog. Second, CI runs evals, scorers and integration tests run against the dev deployment, and only proceed if they pass. Third, a pull request goes up for review and approval, with required reviewers gating the prod target. And fourth, Databricks bundle deploy with target prod, same topology, prod catalog, prod service principal, no clicks in the UI, no drift between environments. Think of one recipe with substitutions written in the margin. Whole milk for the family version, oat milk for the catering version. Same dish, different ingredients depending on the target. The recipe doesn't get rewritten for each version, only the parameters change. That's what a bundle target is, applied to dev and prod. 4 mistakes worth calling out. First, pinning a /version URI in production code that defeats the alias mechanism and forces a redeploy for every prompt change. Use the 8-alias form in apps. Second, holding chat history in a Python dictionary, every restart wipes it, every replica has its own. Put it in Lakebase. Third, initializing the on behalf of client at app startup, there is no user yet, so it crashes. Build the client inside each request handler. And fourth, granting the app service principal can query on the serving endpoint but forgetting can use on Lakebase, the agent will answer, but it won't remember a thing. 6 decision rules worth remembering. Promote a prompt without redeploying the app. Move an alias with set prompt alias. Pin a prompt for an offline eval or reproducibility check. Use the /version URI chat history that survives restarts and is queryable for BI, Lakebase, with Lakehouse sync to Delta. Per user Unity catalog permissions inside an app, on behalf of, via X forwarded access token. All users see the same data, the app's own service principal is enough. And promoting prompts, indexes, endpoints, and apps together from dev to prod, a Databricks asset bundle with dev and prod targets. 3 legs of the production stool. Prompts stored in the registry, versioned, governed, promoted by alias. Memory lives in Lakebase, durable, OAuth-native, sync to Delta for analytics. The user interface lives in a Databricks app, with its own identity, OAuth-authentication, and on behalf of for per-user enforcement. And one Databricks asset bundle ships all 3 from dev to prod with no UI clicks. That's the complete deployment side toolkit. Alright, time to put your knowledge to the test. Question 1. Your team has registered version 4 of the prompt DataDino.prod.exhibit description in the MLflow Prompt Registry. The production app currently loads prompts :/DataDino.prod.exhibit description at production, which points to version 3. Evaluation on version 4 has just passed. What is the correct way to promote version 4 so that production traffic immediately uses it? Is it A, update the app source code to load prompts :/DataDino.prod.exhibit description /4 and redeploy the app? B, delete version 3 from the registry so the production alias automatically falls through to the next version? C, re-register the version 4 template under the name DataDino.prod.exhibit description _production and update the app to load it? Or D, call mlflow.GenAI.set prompt alias with the name alias equals production and version equals 4, no app redeploy needed. Take a moment to think about it. The answer is D. Promotion is exactly one call to set prompt alias, repoint the production alias from version 3 to version 4, and the app picks it up on the next request. The other options either force a redeploy you don't need or break the alias mechanism entirely. Question 2. A senior engineer is building an offline evaluation harness that must produce the same results 6 months from now. Which prompt URI form should the evaluation code load, and why? Is it A, prompts :/name at production? Production is the canonical alias and reflects current behavior. B, prompts :/name at latest always advances to the newest version. so the evaluation will load a different template after new versions are registered. C. Prompts:\name/version. Versions are immutable, so the same number always returns the same template. Or D. Prompts:\name at staging. The at staging alias is reserved by MLflow and cannot be reassigned by users. Take a moment to think about it. The answer is C. Reproducibility means immutability, and the /version URI is the only form that guarantees the same template 6 months from now. Aliases, including at production, at staging, and at latest, are mutable pointers that users can repoint to any version at any time. And just to be clear on option D, at staging is not reserved by MLflow, it's a normal user-managed alias, which is exactly why it can't anchor a reproducible evaluation. Question 3. DataDino's internal RAG app uses corporate single sign-on. Junior curators must not be able to retrieve documents from a Unity catalog volume that only senior curators can read. The app backend calls the agent endpoint, which retrieves from a vector search index over those curator notebooks. What should the app backend send when invoking the agent endpoint? Is it A, the user's OAuth token, read from the X-forwarded access token header at request time, using on behalf of authorization? B, a Databricks personal access token belonging to a senior curator, embedded in the JavaScript bundle? C, the app's own service principal token, granted can query on the serving endpoint for every user? Or D, a shared bearer token stored in an environment variable on the app's runtime container? Take a moment to think about it. The answer is A. Per user Unity catalog enforcement requires the call to actually run as that user, and the only way to do that is on behalf of read X forwarded access token at request time and forward it. The service principal would flatten every user into one identity, and a personal access token in JavaScript is both insecure and unsupported by Databricks Apps. Question 4. DataDino's agent is built with LangGraph and deployed to a model-serving endpoint with scale to 0 enabled. Users report that if they pause for more than 5 minutes, the agent forgets everything from earlier in the conversation. The team needs chat history that survives restarts and is also queryable by the BI team for analytics. What is the recommended Databricks pattern? Is it A, store conversation history in a Python dictionary keyed by thread_ID inside the agent process? B, persist checkpoints to Lakebase via LangGraph checkpoint postgres, and let Lakehouse sync replicate to Delta for BI? C, write every turn to a Spark data frame and use it as in-memory session state across replicas? Or D, provision a third-party Postgres database in another cloud account, peered over VPC, with the password in an environment variable? Take a moment to think about it. The answer is B. Lakebase is the durable store for agent state. It survives restarts and scale to 0. It authenticates through the app's service principal with no passwords in code, and Lakehouse Sync replicates the tables to Delta for the BI team automatically. The dict and the data frame both die on restart, and external Postgres reintroduces all the credential and peering pain Lakebase was built to eliminate. Question 5. Let's test a concept from an earlier episode combined with today's material. A team is deploying its fossil chatbot using MLflow.pyfunc.log model and Unity catalog. They now want to promote the chatbot, together with its vector search index, its model serving endpoint, and its front-end Databricks app, from a dev catalog to a prod catalog using identical infrastructure definitions reviewed in a pull request. What is the recommended Databricks approach? Is it A, manually click through the workspace UI in each environment, taking screenshots for the pull request reviewers? B, write a shell script that issues curl calls against the Databricks REST API for each resource, parameterized by environment? C, use a Databricks asset bundle with dev and prod targets, deployed via the Databricks CLI under CI? Or D, Pickle each resource configuration and upload the artifacts to an S3 bucket per environment for manual restore. Take a moment to think about it. The answer is C. Databricks asset bundles declare every resource in one YAML file: the vector search endpoint and index, the model serving endpoint, the app, with targets that override catalog names and service principals per environment. The CLI deploys the same definitions to dev and prod, giving you reviewable, reproducible promotion with no drift. Manual clicks and curl scripts both reintroduce exactly the drift bundles were built to eliminate. Alright, that's MLflow Prompt Registry, persistent memory, and Databricks Apps as agent UIs in the bag. Subscribe for the next episode of the Databricks GenAI Engineer Cert. Give the video a like if it helped, and I'll see you in the next lesson.